Good afternoon. We are ACT Squared Engineering. Our project is the Logan River Diversion structure. We were fortunate to have two great external PEs and a great faculty advisor to guide us through the design process. They are Chris Slater from JEV Engineering, Bob Fotheringham, who is the Cache County Water Manager, and Michael Johnson, who is a researcher at the Water Lab. Our team consists of Josh Hogue, who is our team leader, Calvin Johnson, who is our finance and budget lead, Jared Justinson, who is our hydraulic and our environmental lead, myself and Clint Marchant, I was the geotechnical lead, Timo Patterson, who is our structural lead, and Tyler Pendleton, who is our documentation lead. Our presentation will go as follows. I will talk about the project overview, I'll talk a little bit about the goals and the scope, then we'll move into the hydrological study and the watershed production, and we'll talk about the design, the Coanda screen design and the structural design. And we'll finish the presentation talking about the budget, the constraints, and the Gantt chart. As I mentioned earlier, we were fortunate to have Bob Fotheringham guide us through this design process. Cache County has collected information that predicts within 50 years there will be a major water shortage within the Cache Valley if steps aren't taken to begin storing excess water. The diversion structure is a small part of the overall plan to collect an additional 60,000 acre-feet of water annually from the Bear River drainage. The total collection of 60,000 acre-feet will take place in two separate projects. The project that involves JCT engineers is to build a reservoir at the mouth of the Temple Fork drainage that will collect all of the water from Temple Fork and also put a diversion structure in the Logan River to divert water to that reservoir. The scope of our project was to design the diversion structure. So our goal was to design a diversion structure capable of diverting 25 to 30,000 acre-feet of water annually. The first task was to site the diversion location. We used three criteria. We wanted it to be in close approximation to the reservoir. We needed enough elevation, so enough head to get the water to the reservoir. And we also looked into land acquisition. As you can see in this picture, this is where we sited it. It's close to the Red Banks campground. It is in close proximity to the reservoir. It also has 100 feet in elevation above the reservoir, so we have plenty of head or plenty of energy to get the water to the reservoir. And currently the land is for sale by a private individual, so land acquisition should be fairly easy.
Next, a hydrological study was made to determine how much the Logan River and Temple Fork streams would contribute to the 40,000 acre feet. Flow data was needed and found from three different sources. First, the USGS gauging station above First Dam, which gave flow data for the entire year. Second, an iUtah station near We Grow, which gave flow data for parts of the year. And third was determined that our own flow data was needed to be collected through an ADCP measurement device. We collected flow data at three different places: the diversion structure site, Tony Grove, and Temple Fork Stream right before it entered into the Logan River. How an ADCP measurement device works is that it's mounted on a little boat, which is then dragged across a cross-section of a river. It measures velocity profiles and the area of the river, thus producing a flow.
These two tables are part of the hydrologic results from the study that Jared has just talked about. The table on top shows the data that our team took as we used the ADCP measuring device. The data on the bottom shows flow data in the Logan River from Trinity Stout, who is a graduate student here at Utah State University. We needed to be able to find the flow data in the Logan River at the diversion site so that we could know how much water is possible to divert at any time of the year. This chart shows the flow data in the Logan River from the year 2014. Most of the data here is from the USGS gauging station just above First Dam. Also plotted is the data that is from the previous slide in the tables that we took as a team when we went up to the diversion site. We needed this data and to be able to take to our external mentors so that we could talk about some design parameters for the diversion structure. The parameters that we came up with were to include a 72-inch pipe that would be leading from the diversion structure towards the reservoir and carry a maximum of 250 CFS at any given time throughout the year. Another important part of our project was the watershed production above the diversion site. We used three main software programs in order to find and analyze the watershed. The first was the USGS StreamStat site. We used HEC-HMS as well as HEC-RAS. First, we used the USGS StreamStat site in order to find the area of the watershed as well as the diversion location. And then we're able to as well find the longest catchment length in that area. Another thing we were able to find was the average slope throughout the entire watershed. HEC-HMS is a program that was developed by the Army Corps of Engineers and is useful to be able to determine the runoff that can come out of a watershed given a certain frequency storm event. We decided to analyze a 100-year frequency storm event. Within HEC-HMS, there are two different methods that we use to be able to determine the infiltration and the transform to analyze the watershed. First, we use the SCS curve number approach, which is based on the watershed area as well as the curve number, as shown here. The curve number is based on the vegetation within the watershed as well as different soil types. Next, we use the Clark unit hydrograph method for transform. This is based off of the watershed area, the storage coefficient, as well as the time of concentration, which is the time that it takes to get the water to get through the longest catchment length. Below shows our final peak discharge that came out of the watershed using HEC-HMS. We found that approximately 2,200 CFS is what would come out of the watershed, if a 100-year frequency storm event were to pass by. Next, we used HEC-RAS, which is a river analysis software also produced by the Army Corps of Engineers. The first thing that we had to do was go up physically to the diversion site and take flow measurements, as can be seen in this image. These are not flow measurements, sorry, elevation measurements. This elevation measurements of the cross-section were necessary to input the data into HEC-RAS so that we could analyze the river with different flow rates. This is an image in HEC-RAS of the cross-section that we measured. It was very approximated. Next, please. And we were able to simulate different flow rates in the river. This shows approximately 70 CFS of water passing through the river. As can be seen, the diversion structure causes the water to pool up behind the structure and therefore can flow over the structure down the Coanda stream, which is ideal for our design. The final thing that we looked at within HEC-RAS was the peak discharge, which we determined to be approximately 2,200 CFS. As can be seen, the diversion structure doesn't really affect the river much when 2,200 CFS is passing through the river.
It was determined that Coanda stream would be the type of diversion placed in this cross-section. How a Coanda stream works is water gathers behind a weir, flows over the weir down a stainless steel wire mesh stream. Water flows through the wire mesh into a detention basin. From there, it is diverted out through a pipe. The slots in the wire mesh are designed in a way that only a certain percentage of water flowing over the screen is diverted. We use the U.S. Borough Reclamation Coanda Screen Effect software developed by Tony Wall to design our Coanda screen. With this software, we were able to come up with the final design. The length of 20 feet, width of 20 feet, a screen length of 9.9 feet, with an angle of 45 degrees. The slot width would be 1 millimeter, and the wire width would be 1.5 millimeters. The wires would be tilted at 5 degrees. With this design, we are able to divert the required 250 CFS.
In addition to data from the hydrological study, the structural design team needed information about site characteristics. JCT² team members examined the soil at the site and found it was composed of silty sands and gravels with many large quartzite boulders. The team also found a bed slope of approximately 1% at the diversion site and a channel which was towards the peak. Using this information, the structural design team set about designing the concrete and reinforced steel for the diversion structure. We chose to use the textbook from the Reinforced Concrete Design class as our guide because this textbook follows the ACI code. The walls and footings of the structure were designed in 1 foot wide sections, which we either treated as cantilever or simply supported beams, depending on how they connected to the rest of the structure. After After designing these sections to resist bending moments, we verified that they were sufficient to carry shear forces. Finally, the design team evaluated the structure for constructability. What we found was that constructability often controlled the size and spacing of the reinforcement bars.
As you can see, here's the side view of the final design of the diversion structure. As a team, we work closely with our external mentors and professional engineers in the design and drawing process. Tyler, Timo, and myself met together weekly to work on the designs and draft the diversion structure. As we did so, we submitted our designs and drawings to Austin at JUB Engineers so that he could provide feedback and useful information in our designs. As Timo said, constructability was something that controlled the design more often than not, and that's something that we learned through Austin. Our preliminary design had many different bar sizes throughout the structure, and presenting that to Austin, he said that that would be a nightmare for the contractor. And so we went back, reanalyzed, and redesigned, as you see here, with number 7 bars and number 8 bars in the head and tail walls, and then number 9 bars in the footing. The construction budget was put together using construction cost calculators. It is estimated that concrete costs will total about $17,000, with most of those costs being due to labor. It is estimated that reinforcement will cost about $4,000, excavation costs will be about $70,000, and finishing costs will be about $6,000, for a total estimated cost of $100,000.
The constraints considered in this project were economical, environmental, political, health and safety, constructability, and sustainability. But the economical constraint, cost, was the biggest factor. The Coanda screen was the best candidate because of its self-clean nature. The long-term maintenance cost would be really, really low. The environmental constraint would be the minimal stream flow. The minimal stream flow is needed to pass by the diversion structure in order to provide enough water for native aquatic species. The political constraint proved to be one of the biggest. With the site being on Forest Service site, it was needed that they would be involved in the planning and building of this diversion structure. The water users, the water right holders on the Logan River are some are the following: irrigation company, Logan City, Pacific Corp, and private users. An example why this would be a big constraint is Pacific Corp. Here's a picture of Pacific Corp. They are the owners of the hydroelectrical power plant on Cutler Reservoir. If water was diverted out of Logan River, they would lose water, which therefore they would lose water to produce electricity and money, causing a big problem and making a big constraint for the project.
The site of the diversion structure is considered to be a remote location, which will decrease the number of people who will come in direct contact with the site. The entrance of the Coanda screen is covered by the screen, which not only prevents logs, sticks, and other debris from entering the pipeline, but also protects from people being pulled in. The site is considered to be mildly visible, which will further decrease people's interest in the site. The location is chosen and it provides for ease of access during all aspects of construction. 4 months construction timeline will be considered for the diversion structure. This does not take into account the amount of time it would take to construct the reservoir, nor the pipeline connecting the two sites. Construction will primarily take place during the winter months because the flows in the river are at their lowest. This is understandably, there will be delays due to weather conditions, although during construction, Highway 89 will not be closed, but will temporarily be limited to one lane of traffic in each direction, or one lane of traffic. Sustainability, JTC Squared has designed and specified the use of a stainless steel Coanda screen, as you can see in this photo. This is a very zoomed in photo because we know how small those slot sizes are and those wires are. Using a stainless steel Coanda screen significantly increases the functionality life of the diversion, which also decreases the amount of maintenance required at the site. As you can see, this is our project timeline. As we go through, you can see what we worked on, and all of the tasks have been completed to date. What we have learned, we've learned how to design a diversion structure, which is a great accomplishment because most of us didn't know what a diversion structure was just a year ago. The second thing we've learned is how to specify a design and the design parameters to be practical for construction. As Calvin mentioned earlier, we also have learned how to apply practical design advice from our professional mentors, professional engineers and mentors directly into the design of the Logan diversion structure, the Logan River diversion structure. This ends our presentation. Are there any questions?
Come on, y'all.
So JUB seemed pretty involved in this. Is this something that they're actually working on, or is this still a hypothetical project?
JUB is involved with it. They have done Cache Valley, a master plan for the water in Cache Valley. They are very involved in it. There is a need that will, because the water is so scarce and becoming scarce, they have done a few preliminary analyses. This was one of the options that they gave us to look at. There are many different alternatives to this project, so we just focused on this one. Does that answer your question?
Yeah, absolutely.
Were y'all planning on fencing off the diversion?
That's a great question. That's actually the sentence I missed in the presentation. I knew partway through I missed one, but as far as being built in the Cache National Forest, it's recommended to not enclose the structure with a fence because the biggest obstacle that we would face with Cache National Forest would be the visibility factor. They don't want it there in the first place, and if they are going to want it there, they're not going to want to see it. That's the advice that we heard and received directly from Bob Fox, is that it wouldn't be fenced off similar to Dewitt Springs, other sites.
But I don't think any young men are going to try to climb on the stream.
That's the advice we received directly from Bob, and that he mentioned specifically that the Forest Service would want it.
Forest Service would want.
They would not, sorry, they would not.
Must be all old guys. That was a joke.
You guys mentioned as you were talking about your design how you have a lot of different sizes for your steel, your reinforcing, how of course that would be a problem for actual construction. But were there any other main snags or problems you ran into as you're doing your project that your advisors were able to help you revise and redo?
Absolutely. That was probably the biggest one that we ran into. The tail wall especially is well over designed with number 7s and number 8s in the tail wall. Another thing that our external mentors and professional engineers helped us with was, as you could see in the drawing, if you could go back to it real quick, that'd be great. In the drawing, it shows how we connect the head wall and the tail wall into the footing with a bonding length of steel. They showed us that as well, and also the overlapping of the steel from the top half of the wall to the steel in the bottom half of the wall. That's also a constructability constraint, having steel sticking up too high or too low. So you have to design to make sure that any rebar that's sticking up is at a safe level. And that's something that they also showed us about the design. Does that answer your question?
Does
this design exist anywhere, actually? You said you got the recommendation, but where did you guys get the idea from?
So for the Coanda screen, there's actually a stream up in Wyoming, Sulphur Creek, where this design is implemented, and it has worked for them fairly well. Also, Weaver Canyon, right before it comes out into the main Wasatch front, there's a Coanda screen spanning the length of the river. So this is a proven technology, and it's highly used right now. It's kind of a hot thing. So I guess I have been used before. Does that answer your question?
Yeah.
Just real quick to add to that, the significant difference between our design and the designs that we had reviewed is the fact, is the sheer size of it. Most Coanda screens only have a diameter of 3 feet, whereas in this design it's 70 feet, 72 inches, 6 feet. So it's a significantly larger structure than has already been.
Well practiced and well presented.